Oh hey, do you want to know how to solve a 2D electrostatic force question? Let's take a look at this question. On an x-axis lies 2-point charges. The first charge, negative 2 nanocoulombs, is 2 meters to the left of the origin, while the second charge, positive 1 nanocoulombs, is 4 meters to the right of the origin. On the y-axis, a third charge, that's negative 3 nanocoulombs, is 7 meters above the origin. Find the electrostatic force, magnitude, and direction felt by the positive 1 nanocoulomb charge. Assume the charges are held in place. Let's start by placing our axis with the grid system where each two squares are equivalent to 1 meter. Let's start by placing the positive 1 nanocoulomb charge 4 meters east from the origin. Now the negative 3 nanocoulomb charge 7 meters north of the origin. Finally, the negative 2 nanocoulomb charge 2 meters west of the origin. Now, let's get the distances out of the way. To calculate the force between A and C, we'll need the distance, which is calculated as 6 meters. Now, to calculate the distance between A and B, we'll need to treat it as a hypotenuse of a triangle using the distance from A to the origin and B to the origin as the other sides. We can use Pythagorean theorem in this virtual right triangle to find the distance is equal to 8.06 meters. To calculate the electrostatic force between two charges, we use Coulomb's law equation. K is the Coulomb constant, which is 9 times 10 to the power of 9 newtons meters squared per coulomb squared. We multiply this constant by the product of the two charges involved, in coulombs, then divide this by the distance between the charges squared, in meters. All the units cancel out to bring you a product with newtons as the unit. This question, we only look for A's forces felt, so we don't need to worry about B's forces with C. A is attracted to both B and C because of how A has a positive charge, while B and C have negative charges, and you know. To figure out what F of A and B and F of A and C is, we need to use Coulomb's law force equation. Now we know the magnitude of each electrostatic force. To get the F net of A, we want to sum up all the x and y components of its forces and solve for the final vector. The AB vector is a little slanted, and since we want to split it into x and y components, we can do so by using trig and SOHCAHTOA. But to do that, we need to figure out what that angle is by also using SOHCAHTOA and the two forces. We now know that it's 60.2 degrees by using the Ka, or cosine theta, is equal to adjacent over hypotenuse equation. Now FAC is already just a horizontal vector, so its y component is 0, and itself is its own horizontal component. But FAB, however, needs to be broken up into x and y components. Now using SOHCAHTOA and rearranging for the unknown side, we can find the x and y components from FAB. This free body diagram sums up the force components the point charge feels. Now this is where
it's all coming together.
We have the x and y components from the two force vectors that affect point charge A. First of all, there's only one y component, which is the y component taken from the force between A and B. Now for the x components, we have to add the FAC vector and the x component from FAB. Using Pythagorean theorem again, we have found that the resultant force vector affecting A is equal to 7.4 times 10 to the power of negative 10 newtons. However, to find the angle, we use TOA and rearrange for theta to find that it's 27 degrees. Therefore, it feels 7.94 times 10 to the power of negative 10 newtons west, 27 degrees north. I hope you've learned a lot during this educational journey. If you'll excuse me, I'm going to sit on this couch for eternity.